Hi, my name is Angela, and today I'll be talking to you about non-biological buffer systems. You might be thinking, buffers? Isn't that what happens when my YouTube videos won't load? But I'm here to introduce you to the world of chemical buffers, which are highly useful not only in biochemical settings like blood and bodily enzymes, but also in many industrial processes that you might not be aware of. Our tutorial today will mostly revolve around one example of an industrial buffer system known as monopotassium phosphate, or MKP. MKP is a soluble salt of potassium and the dihydrogen phosphate ion, which is used in fertilizer mixtures with urea and ammonium phosphates to reduce the escape of ammonia by maintaining a low pH. In this sense, it acts as a buffering agent and also has the added benefit of being a source of phosphorus and potassium. Fun fact, it's also present in Gatorade as a source of potassium, acting as an electrolyte to help regulate fluid balance, nerve signals, and muscle contractions. However, it is not a buffer in Gatorade. At this point, I may have confused you a bit, so here's a clear definition of what a buffer is without the context of fertilizer or Gatorade. A buffer is a solution that can resist pH change when acidic or basic components are added, maintaining a relatively stable pH by neutralizing small amounts of added acid or base. A buffer solution can contain either appreciable amounts of both a weak acid and its conjugate base, or appreciable amounts of both a weak base and its conjugate acid. I say appreciable because both components need to be present in a high enough concentration that it will actually be able to neutralize an appreciable amount of an added acid or base. Another important point is that both components need to be in the solution. For example, the ionization of a weak acid HA on its own will not produce an appreciable amount of A-, while the hydrolysis of A- will not produce an appreciable amount of HA by itself. Therefore, neither 0.1 molar of acetic acid nor 0.1 molar of sodium acetate alone are buffer solutions, but together a solution of 0.1 molar each is a buffer solution. But this whole neutralization business isn't just a magic trick. This might surprise you, but there is a chemical explanation behind how buffers work. Let's come back to the star of our show, MKP. As a buffer solution, the components present would be KH2PO4 and K2HPO4, where the presence of potassium as a spectator ion would leave us with just H2PO4- and HPO4-2-. The solution has the ability to resist attempts to change its pH because one component, H2PO4-, is able to neutralize an added strong base, and the other component, HPO4-2-, is able to neutralize an added strong acid. As seen in these reactions, the addition of an acid or base will produce water and the other component of the buffer system. The overall reaction would be represented as follows. Now that we've established a good understanding of what a buffer is and how it works, let's jump into some questions that may come up relating to buffers and pH. Our first practice problem will be calculating the pH of a buffer solution, which you can imagine would be very important for MKP because its whole purpose is to maintain a low pH for the fertilizer. Here's our question. What is the pH of a buffer solution prepared by dissolving 30 grams of KH2PO4 in a sufficient volume of 0.5 molar K2HPO4 to make 500 milliliters of the buffer? With this problem, the first thing we need to do is calculate the molarity of our H2PO4- ion, since we currently have it as MKP in grams. This is pretty simple stoichiometry, which requires us to multiply the mass of MKP by the molar mass ratio, and then the mole ratio between MKP and its ion. This gives us a concentration of 0.441 molar. From here, we can move on to our good old friend, the ice table. In this ice table, we can put in the concentration of H2PO4- that we just calculated, as well as the concentration of HPO4-2- given in the question for the initial section. At equilibrium, the left side will decrease by X amount, while the right increases by X amount, giving us the final concentrations as shown. However, we can assume that X is very small, as shown by this calculation of the ratio between the initial concentration of H2PO4- and its Ka, which gives us a very large number. Therefore, we can approximate the final concentration of these ions to just 0.441 and 0.500 molar. Later on, we will find this assumption to be valid as X will be very small. Now we can use our known Ka value, which is available through multiple sources including the internet and your textbook, to calculate what X is. Firstly, we'll start by writing out our Ka equilibrium constant expression, which is just the concentrations of the products divided by the concentration of the reactant. Then it's as easy as plugging in our numbers and solving for x. We'll put in 6.3 times 10 to the negative 8 for Ka and the ion concentrations we got from our ice table. This gives us an x value of 5.5566 times 10 to the negative 8, which is the hydronium concentration of the solution. From here, we know that pH is equal to the negative log of the hydronium concentration, so we can use this to do our final calculation. As we can see, x did end up being very small, and that means our earlier assumption was justified. With that said, we have our final pH of 7.25. However, this was a pretty lengthy process, and it wouldn't be very convenient for us to have to do an entire ice table and all of these calculations every single time we needed to find the pH of a buffer. This is where something called the Henderson-Hasselbalch equation comes in. This equation allows us to use just the pKa and initial acid-base concentrations to calculate pH, but it's only valid when two conditions are met. Firstly, the ratio of stoichiometric concentrations must be between 0.1 and 10. Secondly, the stoichiometric concentration of each buffer component must exceed the value of Ka by a factor of at least 100. If these conditions are met, then we are free to use the Henderson-Hasselbalch. Remember how we mentioned earlier that MKP is used to maintain a low pH? Well, in the last practice problem, we found that the combination of MKP and its conjugate base that we used gave us a pH that's a little bit higher than what we would want for fertilizer. So our next practice problem will take advantage of the Henderson-Hasselbalch equation to prepare a buffer solution for a pH that we choose. Here's our question. What mass of KH2PO4, or MKP, must be dissolved in 0.3 liters of 0.1 molar K2HPO4 to produce a solution with pH 6.00? Assume that the solution volume remains constant at 0.3 liters. So this problem will once again use the same equation that we had before as well as the same Ka value. If we look at the Henderson-Hasselbalch equation, we have most of the variables already. pH is going to be 6.00 because that's our goal. The initial concentration of the conjugate base is 0.1 like we were told in the question, and the initial concentration of the acid is what we're looking for. We can calculate the pKa with the formula pKa equals the negative log of Ka. Now all we need to do is plug these numbers in as seen here. We can subtract 7.2 from 6.00 to get them on one side. To get rid of the log, we'll set both sides to the power of 10. Since the initial acid concentration is the denominator here, we can swap it out with the left side, and that quotient gives us an answer of 1.58 molar. But the question is asking us for an actual mass, so we're going to have to use this concentration to get a number in grams. With the knowledge that the volume will stay constant at 0.300 liters, we can do some more stoichiometry to get that mass. Here, we'll multiply the volume by the concentration we just calculated, then we'll multiply it by the mole ratio of MKP to its ion, and finally we'll multiply it by the molar mass of MKP. This gives us a final mass of 64.5 grams, and there you go. That's how to use the Henderson-Hasselbalch equation. I hope you enjoyed learning how to do these super exciting calculations related to buffers, but I don't blame you if all this math wasn't the most interesting. What is interesting is how many applications of buffer solutions there are. The one we explored in this tutorial relates to fertilizer, which of course is necessary to ensure we have plentiful, nutritious food. Another example of a non-biochemical buffer that may be a little bit more relevant to you as university students is actually the process of brewing beer. The first step of making beer involves the mashing of barley malt. During this step, it is imperative that the pH of the solution be maintained between 5.0 and 5.2 to ensure that the protease and peptidase enzymes can hydrolyze the proteins from the barley. If the pH is too low or too high and falls outside this range that is tolerable for the yeast in the barley, it could inhibit their growth or even kill them. Additionally, as the fermentation process goes on, the concentration of carbon dioxide is higher than normal and acidifies the solution by combining with water to create carbonic acid. For these reasons, buffers are added right from the start to make sure the brewing process goes smoothly. Another application of buffers is in the manufacturing of personal hygiene and cosmetic products. It's really important that these products aren't too acidic or too basic because this can cause skin irritations and nobody likes that. Soap has a naturally high pH, so buffer solutions are added to keep it at a pH of about 5.5 because that's the natural pH of skin. In shampoo, citric acid or sodium citrate are common buffers used to maintain a slightly acidic pH that balances out the natural alkalinity of the detergents in shampoo. This way, our scalps don't get burned when we wash our hair. A final example is baby lotion, which incorporates a buffer solution to maintain a pH around 6, which helps prevent bacterial growth and diaper rash. Altogether, buffers are a lot more common than we might realize, and I hope this video helped you understand the chemistry behind how they work, the calculations that are performed to harness the usefulness of buffers, and a few applications of buffers in regular life. Thanks for listening.